Introduction. Turbulent flow is the most common flow in industrial applications and atmospheric phenomena. The random motion inherent in the flow contributes the largest share of fluid mixing and interaction with solid surfaces, for example friction, heating, and pollutant dispersion. Natural ventilation in modern cities, flow-induced vibrations of large civil structures, performance of windmills, etc. keep the topic ever interesting. Hundreds of researches have been devoted to the subject aiming at characterizing this randomness. The main objectives are, 1. To set an exact solution, or at least a mathematical model, to the turbulent flow problem and, 2. To control it, for example, modify vortices and thereby reduce the drag on surfaces. The random appearance of turbulent flow is violated by many well-established evidences. For instance, compared to a random signal, the turbulent velocity signal displays non-zero trends in both the energy spectrum, Figure 1, and autocorrelation, Figure 2, analyzes. These examples, among many others, reveal the existence of organized motions within the irregular background. These organized motions are termed turbulence coherent structures, TCSs. Thus, TCSs are either vortices or uniform momentum regions within the turbulent flow. These structures maintain their coherence over remarkable extents in time and space. The TCSs play a prominent role in the transport and mixing processes within the turbulent flow. Accordingly, few friction reduction schemes target manipulating the TCSs. Furthermore, few researchers attribute large parts of the loading on windmills to the TCSs. It follows that the understanding of TCSs is inevitable in solving and controlling turbulent flows. Energy spectrum of turbulent flow compared to a random signal. Autocorrelation function of turbulent flow compared to a random signal. In this lecture, we focus on the basic kinds of TCSs and their presumable generation mechanisms. We start with the hairpin vortex, which is the elementary building block of TCSs. We characterize the hairpin vortex and detail its popular bursting theory of generation. Afterwards, we discuss the vortex packet sand superstructures, which form the turbulent/non-turbulent interface bulges and contribute around half the turbulent kinetic energy and turbulent transport. Finally, we review the theories of TCS generation in high Reynolds number flows.